Hello, everyone. My name is Marcos Arancibia. I'm product manager of data science and machine learning at Oracle. I would like to welcome you to the first Oracle Machine Learning Office Hours for 2020. So joining us today is Mark Hornick, Senior Director of Product Management for Data Science and Machine Learning. We will be talking today about the Oracle Machine Learning for Python technologies. First things, I'm going to talk about the upcoming session. Then I'm going to go through some of the web questions, and then we get Mark's session. So our next session to look for is in February 12th, the same time, 9 a.m. Pacific. We're going to be talking about the Oracle Machine Learning for Spark. In that case, that's the component that actually works within data lakes and execute computations and machine learning algorithms directly against these big data clusters using Spark for distributing the processing, right? And I'll be doing that presentation myself then, and I'll be joined by Mark. So from the questions we had on the web, the person that had a problem with attending because of a time difference, and yes, as you guys know, all the sessions are recorded and they are posted on the Ask Tom website. So everyone can go there and access and load the slides and also look at the recording from the previous sessions. And the second session is how they can get some desktop or cloud version for testing for Oracle Machine Learning. So for today's session, the Oracle, I would argue there are three different things, right? One is the Oracle Machine Learning is available for free on the free tier of the autonomous data warehousing. So if you go to Autonomous Data Warehouse, you get the free tier, for example, you have access to Oracle Machine Learning there. Today's sessions, Mark is going to explain about the Oracle Machine Learning for Python, in particular, that is in beta today. So any more information on that components and how to get data from there and slides, again, explanations, you can always go to the oracle.com/go-to/machine learning, and you'll find all the different technical details there. And then this is the always free cloud tier. So if you have not done so, I would encourage you to go to oracle.com/cloud/free and take a look at that free trial and the always free services. You're going to find the Autonomous Data Warehouse there, and you do have access to the Oracle Machine Learning at that point. Now I'll leave it to Mark to talk about the Oracle Machine Learning for Python. Basically, the idea is how to use Python and integrate the Python language with all the performance that the Oracle database can give you and all the algorithms we have there. Thank you very much, Mark, for joining, and please take it away.
All right, thank you very much, Marcos. Hello and welcome to this session on Oracle Machine Learning for Python. My name is Mark Hornick, the Senior Director of Product Management for Oracle Machine Learning. And with Oracle Machine Learning for Python, or we refer to it as OML for Py, it's new functionality that's coming soon. That's the most that we can say as far as the expectation date. But it's for Autonomous Database and other Oracle platforms. And so what this session will largely be a series of demonstrations of the various aspects of the functionality. But first, I'll give you a brief introduction to OML for Py, just so that everyone has some common background in what OML for Py is all about. So, this is the Oracle Safe Harbor Statement. You've probably seen it many times before. The following is intended to outline our general product direction. So I suspect that if you're attending this session, you know what Python is, right? It's an interpreted, object-oriented, high-level general-purpose programming language. But our interest today is the fact that Python, while providing a rich ecosystem consisting of thousands of open-source packages, it enhances data scientists and Python developer productivity. And for us, we're interested in the data science and machine learning aspects of that and how we can make those more effective for the data scientist and Python developer. However, we'll find that Python has some challenges when working with bigger data. And so our interest is how to enable users to work with larger volumes of data and deploy their solutions easily, all through Python. Now, OML for Pi is part of the larger Oracle Machine Learning product family or platform. Last year, we rebranded our components of Oracle Advanced Analytics and others under the umbrella of Oracle Machine Learning. So OML provides interfaces for three popular languages: SQL, R, and, as we'll be discussing today, Python. For interaction with Oracle Autonomous Database, we provide the Apache Zeppelin notebooks with a SQL interface, and we'll be expanding that into Python and R as well, with the OML for Pi and the OML for R, which formerly was Oracle R Enterprise. The Oracle Data Miner user interface is a SQL developer extension that enables users to create analytical workflows through a drag-and-drop interface. Some of you may have used that already. And Oracle Machine Learning for Spark, formerly Oracle R Advanced Analytics for Hadoop, provides data preparation and machine learning in the big data environment. Now, a component that we had made previously available only to Oracle applications internally is OML microservices. And this the success of this feature has led us to wanting to make it generally available for end users. So that's also coming soon, and that's supporting image and text and scoring model management features as well. But today, we're going to focus on OML for Pi, Oracle Machine Learning for Python. So to set the stage as, what are the issues that we're trying to address with Oracle Machine Learning for Python? A lot of data is stored in relational databases, right? For example, Oracle databases. And users who want to work with that data need to get it from the database to the Python engine. So one method of dealing with that is through flat files, right? Perhaps we ask IT or the DBA for an extract as a CSV file. And this can take a few iterations, right, to get the right data to solve a given problem. You might not have gotten enough data, you might have gotten the wrong columns or the wrong tables, and so this all adds to project delays. And once the results are available, they need to be placed back in the database. But some users might be lucky enough to have programmatic access to their database through, say, ODBC type of interfaces, or for Oracle database, the package CX Oracle that's optimized for Oracle database. Still, for larger volume data, this poses several problems for users, right? The first one is the time that it takes to extract and load the data or pull it from the database into Python memory. So we'll call this access latency. Next, we need to ensure that the data will actually fit in memory and that there's enough memory left over to do meaningful processing. Then even if we have a powerful machine with a lot of processors, most functionality that's provided, sort of the standard functionality, is single-threaded with Python, as with other open source tools like R. So the performance might still suffer even in the face of sufficient resources. Now, granted that there are various packages available for taking advantage of parallelism, those that are implemented in a parallel way, but many of these also require special coding. So ideally, developers would prefer to remain in the Python language and have all of these capabilities available to them immediately without having to go through any special coding or interfaces, and not having to learn other languages, perhaps like SQL. This avoids paradigm shifts and can often improve productivity. So when a solution is finally at hand, the issues of backup, recovery, and security need to be factored in as well. More moving parts clearly results in greater complexity for each one of these. And finally, how do we get this solution into production? Too often, developers end up implementing the same plumbing for each project to support production deployment. And this results in a lot of time that's spent in developing and testing software that should really be considered a solid infrastructure that they can simply use. So, this brings us to Oracle Machine Learning for Python. It's intended to be a high-performance computing environment that's leveraging Oracle database to support this type of scale and faster access to your Oracle data. It's also providing a set of in-database parallel distributed machine learning algorithms, right? You want to be able to build more models faster, score larger volumes of data faster, and overall have increased productivity through various automation capabilities like automated data preparation or partitioned models or even integrated text mining. When you develop your Python scripts and you produce various Python objects, think of machine learning models, where do you store those? Do you store them in flat files that have to be managed separately? Or with Oracle Machine Learning for Python, you can store them in the Oracle database. And so this also facilitates collaboration by allowing you to hand off data science products from the data scientists to, say, the application developers very easily. And a new feature that is in Oracle Machine Learning for Python is automated machine learning. And so the goal here with automating this aspect is to enhance the data scientist's productivity, enable non-experts to use and benefit from machine learning, and also to produce more accurate models faster. So this notion of including Python, and as we've done in the past, R, is to empower data scientists with open source environments. Now, the four areas that we're going to cover in the demonstration, which will be coming up next, are what we call the transparency layer, the parallel distributed algorithms that are in the database, embedded execution, and AutoML. So with the transparency layer, what we're doing is creating proxy objects for data that exists in Oracle database. We're overloading native functions in Python, and we translate those into SQL behind the scenes. So we take advantage of the database as this high-performance compute engine. And the user gets to use familiar Python syntax. Now, with the parallel distributed algorithms, we are achieving scalability and performance by taking advantage of powerful infrastructure in the Oracle database that can leverage these advanced machines like Exadata. And so we're exposing those in-database algorithms through a Python API. With embedded execution, we're saying you've written some Python scripts and you'd like to be able to put those into production easily, perhaps even invoking them from SQL and getting the results back as database tables. And so we're allowing you to manage and invoke your Python user-defined functions in Oracle database, even invoking those in a data parallel and task parallel fashion, where the database is controlling the execution of those Python engines. And certainly in the on-premise case, you're able to use whatever open source package you'd like to augment that functionality. With AutoML, you'll see that we have this notion of model selection, or what will amount to algorithm selection, feature selection, and hyperparameter tuning, and we'll see that in action. So with that, I'm going to move to demonstration, and this is going to be in a Zeppelin notebook. And the reason why we're using the Zeppelin notebook is that we're first going to make OML for Pi available as part of the autonomous database and using the Oracle Machine Learning Notebooks interface for that. And since the OML Notebooks is based on Zeppelin, it makes sense to do that here as well. So, we've talked about what OML for Pi is. In this demo, we're going to start off with the automated machine learning so that you can see what we're providing there. The in-database algorithms for model building and scoring, looking at how do we create database tables and retrieve data. Also, transparency layer functionality, so that you get the scalability for some of the data preparation and exploration that you'd like to do. And then embedded Python execution, where you can actually define a user-defined script, store it in the database, and execute it from Python or from SQL, and we'll take a look at that as well. So the first thing that we do is we connect to Oracle database. And with that, we're going to import OML, and we're going to get the AutoML imported from the OML package itself. We're going to connect. Now, if we're in autonomous database, this is a step that you wouldn't have to do. It would happen automatically. But because this is the beta software that we're using, and it's actually installed on-premise, we're going to connect explicitly to the database and then check if the connection is there, and we see that it is. So the next thing we're going to do is get a proxy object for a database table. Now, we're going to look at a data set that's shipped with Python itself, the breast cancer data set. And we've already populated this in the database because oftentimes the data that you have is already existing as a database table. So we'll invoke OML sync to get the proxy object for this particular table, where our goal is to predict whether or not a patient actually has breast cancer based on various predictors. So once we get that, we'll check out the type and the shape, and then do some transformation on that, splitting the data into train and test, and setting that all up. So we see we've got about 570 records, 31 columns, and that our proxy object is of type OML data frame, right? And so even after we get finished doing other transformations like splitting the data, we are still dealing with the OML data frame. What this means is that we have the ability to now manipulate this handle, this proxy object, as though it were a pandas data frame. But these operations now are going to be occurring in the database. And so we'll see how that works out. All right. So you can see some of our data here as well. AutoML. So I'm going to kick the first one off and then talk about it, because that takes a little over a minute to do that. So we'll be all set there. With the AutoML, the process that you go through with that is, one, you want to identify the most appropriate algorithm for using the model selection functionality. And then once you know what algorithm you should use for your data, let's get the best set of predictors or features that will support that algorithm, so feature selection. And once we have both of those, then let's tune a model. It's the hyperparameters that we provide to the algorithm, so we get the best performance, best accuracy, or whatever scoring metric that is of interest. Now, if we look at the automatic model selection or algorithm selection, we have a number of different algorithms that we can choose from. And if you're dealing with a classification problem, maybe you want to check all of them: decision tree, generalized linear model, naive Bayes, et cetera. And that can take a bit of time, right? You've got to understand what those algorithms are, what is the preparation that's necessary for the data preparation for each of those, and then the various parameters hyperparameters that you can provide to those algorithms. And there can be a lot of iterative, repetitive work to figure out what is the right algorithm for your particular data. So what we want to do then is to use the AutoML to do the model selection. And so in this, here we have an accuracy score metric that when we invoke model selection, the select function, it's going to go through and tell us what is the algorithm that is most appropriate for this particular data. And what we see here is that we've created a model selection object. We've said the mining function is going to be classification in this case. We have the score metric. We're just going to use simple accuracy, but as you see up above, there are a number of different score metrics that you could supply, whether you're dealing with binary classification, multi-class classification, or regression, and even the degree of parallelism that you'd like to use. So here I'm selecting 8 so that it processes many of the model builds that are occurring behind the scenes and the type of intelligence or meta-learning that's going on to do this selection. So we provide our proxy objects, the breast cancer train X and train Y. This matches sort of the Python approach for passing data, and that we want the top model. So this is actually going to go through and figure out what is the best algorithm. We see it support vector machine here, and by looking at the model itself, we can see what are the predictors that were used, and all of that processing to go through a range of models, different algorithms, is done behind the scenes, and you can simply leverage this in the next step, which is going to be dealing with feature selection. However, one of the things that you might want to say is, well, how close were the different algorithms in terms of their accuracy for that? And so here you can say that you'd like to get the ranked models out of this and invoke select on the data and specify the number of models you'd like to return. And I should point out this tune parameter here. Tune is saying, do you want to actually tune the best model as well? So it's kind of a hybrid functionality in that it not only is selecting the best algorithm for you, but it can also produce a model that's pretty much ready to go in that. And so once we have that, what we'll see are the various accuracy measures for each of the algorithms, and you can see how they compare to one another. So as we're waiting for that to complete, I'll just mention the automatic feature selection. So as I said a moment ago, we are going to choose based on an algorithm, what are the features that are most appropriate for this? And so not every algorithm will use the exact same features the same way. There are different patterns that are present in different combinations of features. So you might want to have a different set based on the algorithm's capabilities. And with this, that's what automatic feature selection is going to do for us. But it looks like our previous selection completed. So we see the ranked models. We have the SVM linear as coming out as the top algorithm up here at the top. Neural network was a close second, GLM ridge, and then SVM Gaussian. So you can see why it was recommending the SVM linear based on the score metric that we identified. All right, so let's go back to automatic feature selection. And I'll just kick this off. And we see that for the automatic feature selection, we're again saying it is a classification problem. We have a score metric of accuracy, and we're again going to use our 8 CPUs. Then we invoke reduce. And notice where we're providing the SVM linear algorithm and our data set. So this is going to give us the set of features that are most appropriate for this particular algorithm against the data that we have. And then we're going to reduce our data set, the predictors, based on what is recommended. And here we see the selected column. So from the original 31, we have about a third of those at 10. So now the next step in the process is hyperparameter tuning. And hyperparameter tuning is one of those arts, if you will. It's not necessarily always clear what are the set of parameters that are going to produce the best result. And so what we at Oracle have done, and Oracle Labs in particular, who's provided the underlying technology for this, is again a type of meta-learning, where we're using a gradient descent approach to zero in on the right set of parameters that should be provided to the algorithm to get the best accuracy. So in this case, I'll just kick this off as well, we're going to create a model tuning object. Again, say that it's classification. We have parallelism set to 8. And we're going to tune it saying that we have an SVM linear algorithm that we want to use. Notice that we're using our reduced training set. We provide the target, and then the score metric of accuracy here. Now, when this completes, you'll see that we're going to look at what the best model is. And so, of course, it's going to be a support vector machine, since that's what it was doing. But we might want to look at some of the other models that were tried out. And so I'm just going to show 2 of these here. Here we selected the best model, right, out of the results, but we can look at all evaluations. And this is going to tell us that, yes, the very top one had 0.97 accuracy, and these were the parameters that were selected, so we're using an SGD solver for that. The next one was 95%, and that was an IPM solver. So you could continue with that. They're all there, but that gives you an idea. Then you could say, well, given the test data, what is the accuracy on that? And so interestingly enough, the accuracy on the test is even better at 98%. So that's coming back from the score function. Now, when we talk about hyperparameter tuning, you may want to offer a different space or a more specific search space than what the technique is doing behind the scenes, right? What the auto-tune is doing. And for that, you can actually specify a search space with a range of values. And here I'm going to show, just doing this for a random forest algorithm, where we say, well, what is the sampling ratio options we want to try, the number of trees, the impurity metric. And when we run this, it's going to tune the model for that. Now, of course, we're using the same reduced data set that we used for the SVM, and we might want to do a different feature selection based on the random forest algorithm. But for the expediency, I'm just using the same data set. But we're passing in this search space, and then we'll look at the results that come back. The key thing to note is that even though you specify a given search space, the technique that we're using actually may try the ones that it would do anyway. And in some cases, if your goal is to have the best, say, accuracy, it might not be from the parameters that you've specified. So your actual results here, where you look at the various settings, may be different from what you initially specified. Now, another interesting aspect is that some of the parameters you may want to specify based on data-specific values, like the number of features or the number of samples or rows that are there. And so for that, you can also specify the search space with the NR_features, and then incorporate that into some computation. And so when we rerun that, we'll get a different accuracy. This one is a little bit less than the one that we had before, but that's because we're giving it some other options to consider. All right, so that takes care of the AutoML, the automated machine learning features. We're now going to turn our attention to the more direct way of manipulating and creating models in the database. So these will be using the in-database machine learning algorithms. And the first thing that we might want to do, as we were looking earlier with feature selection, is compute the attribute importance. What is the ranking of variables? We can do this explicitly. And the data set that we're going to work with is the iris data set. It's small, it's well known. It has to do with the dimensions of flowers from 3 species of iris flower. So notice that we're going to do the OML sync, and this will get us the proxy object for the table in the database called iris. And then we're going to drop the species column, so we get the predictors, and we're going to assign to Y just the species column as our target. And then notice also that if we wanted to display this in Zeppelin, we're going to first pull the data back to the client. In this case, we could use head, the overloaded head function, or since iris is only 150 rows, we're grabbing all of it. But then zshow puts us in, puts the result into the table format that Zeppelin provides us. Okay, let's see, did I actually run this? Maybe not. Let's do that first. Okay, so now we've got our data set, and we're going to define an AI object here and invoke fit on that. And so this is going to use the in-database computation. So we're not pulling any data to the client to support this. So whether it's 150 rows or 150 million rows, this is all occurring inside Oracle database. And we see the result that we have here, showing that the petal width is the most important, followed by the petal length and the sepal length with that. And it's a very quick operation, as you'd expect for such a small data set. But even for larger data sets, it will be dramatically improved over having to extract the data from the database and then perhaps using a non-parallel implementation, because the in-database algorithms are parallel distributed, taking advantage of powerful back-end hardware. All right, so let's build a random forest predictive model explicitly on iris. And so we're going to prepare our data here, and notice that both of these are also OML data frames. So our original iris DAT is one, and what we have done the split as well, each of those are data frames. So we're not actually pulling any data back to the client. So the next thing that we'll do is build the random forest model. So we're going to create a random forest model object, specifying the max term, max depth for the tree, and then we'll fit that with the training data set. And here we see the random forest model that was produced. And also we get the attribute importance as part of that model build, so you can see what random forest thought of the various predictors. Right? We can use the random forest model to predict, right? That's one of the reasons for building a model. And so in this case, we have the predictions coming back by invoking the predict function on our model. We're using the proxy object, and we're going to do that for the test data, dropping the species, because we only need the predictors. And then we have the supplemental columns. Now, supplemental columns are really interesting and important and valuable for this. If you're dealing with a relational database, typically relational databases, the relational algebra does not specify ordering for the data that comes back. If you want ordering, you explicitly do a sort on that data, and sorts can be expensive, especially for large data. So you only do it if it's essential. Well, in the world here of mapping these from database tables into Python well-ordered data frames, we want to be able to associate either the specific target, so that we can do a confusion matrix, as we'll see in a moment, or a case ID, a unique identifier associated with each row, so we can join that back with other data. So in this case, we're adding a number of the predictors in and calling those supplemental columns. And you see as we execute that it comes back with our predictions and the original data values that we've asked to have returned. So let's use this now to compute a confusion matrix. We'll use the overloaded crosstab function, and we want to use the species column and the prediction column, and we're going to be pivoting this data. So as we execute this, in the database, it's taking our result set for the predictions, and then doing this computation, the crosstab, and sorting the results so that we can see that the model did pretty well. Only a single error was made in one of the samples. Okay. Another thing that's fairly interesting is to work with data to identify anomalies. And with Oracle Machine Learning, we have an algorithm called one-class SVM, a variant of our support vector machine. And it allows us to identify anomalies in the data, ideally based off of only normal samples. But even if you have mixed data, it will still identify those that don't sort of match the rest very well. And so when we do a prediction, we'll have a value of 0 predicted if it's considered an anomaly, or a 1 if it's considered normal. So here we're going to use the entire iris data set, and this is how we specify that. So we have some settings, and we're going to say that the outlier rate is 5%. We only want 5% of outliers identified. You don't want too many of those. The SVM object, it's saying that it's an anomaly detection mining function. And for the SVM kernel, we want to use the linear kernel for that. And we're going to fit that on our proxy object, iris. And we have no target specified because this is an anomaly detection operation that doesn't require a target. So we just built this model, and we can see what the various coefficients are for this model and what the settings were that were used to it. But let's use this model to predict. So in this case, we have the SVM model, and we're going to invoke predict, again on our proxy object. Of course, we're just using the original data set. And what we have here is additional supplemental columns, and we're going to add those, the predictors and the target, so that we can compare which ones were actually considered the anomalies and whether or not we should analyze them further. So here we're just going to look at the predictions that come back from this. We're going to pull the top, 5 or 6 rows here, and then show those with the Z-show as before. But if we want to get the specific anomalies, we'll look for the predictions where they were 0. And rerunning that, we see that the result is, of course, an OML data frame. The size, we have 150 rows, so the original iris shape, and the anomalies we had 8. And so this essentially gives us our 5% of anomalies. And if we look at these, we can see that the one that is identified as the most anomalous here at 60% probability is a bit on the large size, right? And so this is considered for versicolor, perhaps not as representative as the other entries. Okay, so that was looking at the modeling aspect. Let's turn our attention to the transparency layer and dive into a few things in a little bit more detail. We've been working with these proxy objects a lot now. And one of the things that you might want to do is say, I want to create a table. I've got to get my data that I have locally into the database. Well, how can I do that? And what are my options for that? So in order to illustrate this, I'm first going to show how we can get data out of the database. If you've got data stored in a table or a view, you could invoke the pull function like we did earlier, and this will give us the actual Python, the pandas data frame. And we'll see the type of that coming back here. Then we can look at that data as well, because it's going to be a standard pandas data frame. So if we wanted to create a temporary table in the database, you could say, well, I'm just going to be doing some quick and dirty exploration of this data, and I want to transform it, but I don't want to have to actually create a table that I have to delete later. So I'm going to push this data to the database, the pandas data frame, and this is going to create a temporary table such that when I terminate my connection to the database, remember that's what we did at the very beginning here, we established a connection to the database, that it will automatically clean up this table. So I push that, and if we run this, we'll see that the type is OML data frame, and its shape and the columns that we have exactly as we would expect. It's a proxy object that we can manipulate as though it was a pandas data frame. Now, you could say, can I create a persistent table, though? How do I make sure that that table stays around and give it an actual table name that might show up in SQL Developer or something? So for that, you can use the OML create function. And of course, you can drop tables too. So OML drop here, we're just doing that to make the script executable or repeatable. But here we're going to pass in the local iris pandas data frame and giving it the table name of new iris. So here we will look at the data type of that and show the result. And there's nothing all that surprising here. It's what we expect to get. It should look exactly like what we had before, only this time it's an OML data frame. So as far as the functions that are overloaded in OML for Pi for data frames and others, some of the array types, this is the set that we have currently enabled, and it scrolls down a bit too. So there are both some statistical functions and data munging type of functions. And we'll look at a couple more of those as we go through. So if you look at the overloaded aggregate functions, here are just a couple of examples where they were looking at min, max, mean, median, et cetera. So the statistics that you'd like to get back on data. And again, this is all being done in Oracle database on the data that's already in the database. So we don't have to pull any data out to get these types of results. It's very efficient from that standpoint. If we're looking at filtering data, yeah, you can create masks, various logical constructs, and then invoke those as well. And this can occur on individual columns or on the entire data set to retrieve certain rows of that data. Joining is another very common operation that one needs to do in preparation, data preparation for data science and machine learning in particular. So we're going to create a simple data frame and push this to the database as a table. So I just made some descriptions of what these three species of iris flower are. And so this will show up as a table. And then I can invoke the overloaded merge function to say on iris, I want to merge or join this iris description using the species as the join key. So if I run that, I can pull back some of the results there, and we see that we have the original data plus the new column that's there. And you can build on top of these as well. So if you got IRIS2 and you then said, well, I want to merge yet another table with that, you could continue IRIS3 or whatever you wanted to name that resulting Python object, and then do some computations on top of that, or provide it to the algorithms for model building. So this really makes life a lot easier for Python developers. Now, another function in database, sort of statistical function, correlation. And this is where we can simply say on IRIS, compute the correlations between the various numeric columns. And what we see here is that the petal length and width are highly correlated in this case. Visualization, another very important aspect of the data science process. So we have a couple of functions that are overloaded. I'm going to show the box plot and the histogram functions. So in this case, when you're trying to do some of these operations, the statistics that need to be computed can be somewhat intensive if you have to pull the data and do that locally in a non-parallel way. But if you can use the database, Oracle database, as a high-performance compute engine that takes advantage of things like indexing and query optimization and parallelism and even partitioning at the storage level, you can get these done a lot faster than you could if you had to bring that into your, say, laptop. So we have an overloaded function, box plot, and all the statistics are being computed in the database here. And the only thing that comes back to the client are the few data points that are necessary to actually to produce the plot. And this, as you can tell, this is a very small number of points that are necessary per column. So that's a very efficient way to return the results. The same thing is true for the histogram function, or hist. In this case, we do all of the computation, the binning and whatnot of the data, and getting the results directly in the database, and only return those data points that are necessary to produce the plot, which is quite a limited number, which is exactly what we want to see. Another process in the data science flow is creating derived variables in support of machine learning, or even just exploration. So here, we may want to say, I want to identify petals that are large, and we're going to say that they're large if they're greater than, the length is greater than 5 and the width is greater than 2. So I can create that. I can see what the type is, and then concatenate not only this column of logicals, but also let's square the sepal length and have that as a derived variable as well. So if I execute this, notice I'm always dealing with the OML types here, because this is in an in-database object, a table. And I can see here that I've got is the petal large as a Boolean, and the squared sepal length as well. So now this can be used for providing to a machine learning model. Describe is also overloaded, so I can invoke this on our IRIS2 dataset that has these additional columns, the sepal length, square in particular, and we get the various statistics. So all of these statistics are being computed in the database. Crosstab and pivot are also overloaded. So here's a simple dataset that is describing handedness for a certain task of speed and accuracy. So we're going to push this data frame to the database, producing a temporary table, and we see the contents of that. And then maybe we want to find the categories that most entries belong to across gender and hand, left or right. And so we get those, and we can just sort those easily enough. In the case of crosstab, another example where we want to get some specific stats on gender relative to handedness or across both of those. Pivoting is a very important operation for data preparation as well, and we can even combine that with some statistical computations. So here we're looking at what is the max across each of the combination for gender, hand, and with speed. Okay, so that's enough for the transparency layer. I think you get the idea of that. Let's talk about data stores, another capability or concept within OML for Pi and also OML for R, or Oracle R Enterprise. The notion of a data store is the ability to store, in this case, Python objects in Oracle database. So you don't have to write them out to a flat file and manage that flat file elsewhere. So we're going to go through a couple of examples with this so you see what's possible here. I should also say, if you want to understand why do I need to do this, why would I want to use data stores to store things in Oracle database? Well, one is so you don't have to manage the flat files independently. They can all be within a single repository, which is very neat and efficient. But another important aspect is that if you want to pass objects when using the SQL API, which I'll show the SQL API at the very end, you can't pass non-scalar objects. So if you wanted to pass a model into one of your functions that you've built elsewhere, you would do that using a data store. Or maybe you have another complex object that you'd like to pass into to your user-defined function. You can simply pass the name of the data store as the argument to that function and then load those objects directly. So let's see what that means. Well, here we're going to use the ds.save operation to store two objects, the pandas data frame, the local iris, and then the OML handedness entry for our handedness proxy object. And we're going to call this the MyPython datasets. We give it a description and say, well, if it's already there, overwrite it, and we'll start over. Then we can show the contents of all of the data stores that we have. And we really only have one at this point, so that will show up. We've taken these objects and we've loaded them into the database. So we see how many objects are in our data store, the size of it, when it was created, and the description that we provided as well. So let's add another object to this existing data store. So we created iris2, recall, and that was another proxy object. And we want to store that in the data store. So we're going to add that and say append is equal to true. And so now, if we execute this, we see that we have three objects in here, and the size has increased a little bit on that front. So within a given data store, we can interrogate what objects exist there. So using describe on my Python datasets, we see that we have three objects, iris2, iris, and OML handedness, and their corresponding class, their size, the number of rows that are in them, and the count as well. We can delete objects from a given data store on an individual basis. So here, if we wanted to remove the iris dataset, we simply specify that, and it is no longer part of that. Okay, so data stores are very useful for working with, especially the embedded Python execution, which we're going to be covering in a moment, just next. But first, I want to talk about the Python script repository. So the Python script repository is one that allows us to store user-defined functions, or scripts as we refer to them, in Oracle database. And by storing them in Oracle database, it means that we can invoke them through embedded Python execution by name. And this allows us to perhaps hand off scripts between data scientists and application developers, or allow us even just to load scripts, store them there for future use. We can load them back into the client and execute them. So there are a lot of possibilities for taking advantage of this. And you can also grant and revoke access to these. So there are access permissions not only on the Python script repository, but also the Python object repository that we have. Okay, and with the data store. So The script repository is going to be illustrated as we go through the embedded Python execution examples. So just hold on a second, you'll see how those get invoked in a moment. With Python, we can say, let's have as our best practice workflow, build a function, or use Python interactively to develop a script that solves a particular problem, and then put that in a function, and then see how that behaves on the server side. So in this case, we want to have a function that builds a linear model. And so we're going to import sklearn. So notice that you could import packages and whatnot if they're existing on the backend Python engine. And we're going to have also an image that's generated. So we're going to work with matplotlib. We'll build a very trivial model that takes in a pandas data frame and predicts the petal length given the petal width. That's, of course, our iris data set. And then we'll do some prediction and a scatter plot of the results. And so if we execute this just in Python, right, this is not doing anything on the database server side, we see the type of result that we get. Okay. Now, let's invoke this using a function in embedded Python execution called tableApply. What this does is say that we want to have our function executed by the database in a database-controlled Python engine. So the database is going to spawn a Python engine, load our function into it, pass in data, in this case, the entire proxy object data iris, into that function, execute it, and return the result. So if I execute this now, all of that processing is taken care of. Remember one of the things I mentioned at the very beginning, that having to re-implement the plumbing to support deployment, the spawning of Python engines, the keeping track of all of the different pieces where the data is and whatnot, can be a real impediment to getting things into production. This makes it very easy from the Python perspective, but as we'll also see, doing it from SQL is even better for a lot of applications that are SQL enabled. Now, the model that was produced, we can pull that model back as well and see that indeed we have the linear model that is available and what its description is, and even see the coefficient of that. Now,
Mark,
yeah, go ahead.
There are many questions. There are many questions about the embedded Python, and some of the questions had to do with where the model is saved, where is the engine running it, right? Where exactly is the engine running the Python code? Whether people can use scikit-learn, pandas. So I think that's the idea, right? That's what you're showing. You can use all of those things. Mm-hmm. And I was saying that people can save the results to either, a local file system, because at that point is whatever your choice in your code, right? Or you can save it as an object in the data store, right?
Oh, absolutely. Yeah, those are all great questions. So as far as, where is the Python engine running? When you have a client, okay, so that can be anywhere you'd like it to be. If it's on your laptop, you can have a client that connects to your Oracle database, and you're operating from that. So anything you could do in Python, certainly you can do right there. When we're talking about embedded Python execution, these are Python engines that are under the control of Oracle database. Now, when we're talking about an on-premises type of deployment of this, you have the Python engine that, let's say we're talking about Exadata. You would actually install a Python engine on each node of your Exadata. And if you wanted to use third-party packages, you would install those as well on each of those nodes. And what the database does is to invoke those Python engines through an external process. So it's using what we refer to as an XProc that will initiate the creation of that database, and it manages that. So if you're on Exadata, then those engines would be executing there. When we come out with the Oracle Machine Learning for Python on autonomous database, there's a slightly different architecture that gives equivalent functionality, but is located differently from the cloud perspective. And so we'll talk about that more once we get closer to the release of that. But essentially, these will be executing in VMs that are sort of co-resident with the Oracle machine learning notebooks. And so we can explore that further in another session. But I think that should answer the question for where these are and whether or not you can use third-party packages, at least on the on-premises version. When we're dealing with standard packages for Python, anything that's in the Python engine itself you have available to you, and there are a number of other packages that will be sort of included with the Oracle Machine Learning for Python itself, like matplotlib or pandas and whatnot. Those are there. If you want other packages in an on-premises installation, you can install whatever you'd like. And when we are dealing with autonomous database, we'll be providing a small set initially and growing that over time so that users can work with the packages that they would like. Were there any other questions, Marcus?
There were like 50, but I've been answering them
okay.
over the chat. I've been answering over the chat, so no worries.
Great. Okay. Well, thank you for doing that then. All right. So let's go to the next step of this. So what we did in the previous example for embedded Python was to pass in the function object, right? The build lm1 function object directly, as opposed to the name of a function from the Python script repository. Well, here, using the script create, we have build lm1, and we're going to give the function object and load this into the script repository. So by executing this, you see that, yes, we have build lm1 that's provided, and we've just added that in as well. And now we can use that by name to invoke our embedded Python execution function. So go back to OML table apply. Data is equal to iris, and the function is now a string, not the function object. And when we invoke this, we see the results that we have coming back. We've got the object and the regression model itself, and we can look at the coefficient coming from that. Now, if we wanted to do scoring, one of the nice benefits of the embedded Python capability is that you can do data and task parallel execution. What does that mean? Well, from I'll focus on the data parallel part. Think about you have an open source Python algorithm. Maybe you've used XGBoost or you've done something else. And you can build the model, but you really want to score it at scale. You've got perhaps hundreds of millions of rows that you want to score on this in batch. Well, you could do it one at a time, right? And it would take a bit of time. But if you could do that in parallel, chunking that data, using what we refer to here as row apply, you could spawn multiple Python engines to be executing in parallel, have the data fed to them that should be scored in parallel, and get the results back in the database in parallel and present that result to you as a single table. So that's what we're doing here. We have the definition of a function called score lm1. We're passing in a pandas data frame. We're passing in the model object in this case because we're working directly from Python. And then we're going to predict that model and produce the result that we pass back, and we see that this is what it's going to produce. With the row apply, we pass in the data frame, I should say the proxy object, iris. We specify that we want to do 10 rows at a time, right? The iris dataset has 150 rows, so that means that we're going to have 15 invocations of our function, which is score lm1, and we're going to pass in the model object to it, and the result that we want to get back is to be a table, and what that should return is the species, the petal length, and the predicted petal length, so that we can see that. And as we execute that, that's exactly what we get by looking at the head of the result. Now, a different aspect of embedded execution that's also data parallel is one that involves group apply. Now, group apply here is saying, based on a particular column or set of columns, I would like to partition my data into different subsets of that data, and then build a model or execute my function on each partition of that data. So in the case of building models using the iris data set, I can invoke group apply, pass in iris, and say, I'm going to use my original build LM function, the same function, interestingly enough, you don't have to change it, but I'm going to partition that based on the species column. I'd like you to do this in parallel with parallelism of 3, so spawn 3 Python engines to support this. And because we're going to be using the data store, let's actually connect back to the database because we need to support that. So if I execute this, it's going to go to the database. Database is going to spawn 3 Python engines. And notice that we get back 3 models, one for Setosa, one for Versicolor, and one for Virginica. Okay, and we could then use these models to do scoring as well. So this could include anything, right? It doesn't have to be model building. It could be data exploration. It could be data preparation. It could be any number of visualization things that you'd like to do on your data as well. Now, we can change our user-defined function to use the data store. In the previous example here, right, we specified OML connect true, but we're still returning through our original build LM the actual models for this. What I'd prefer to do in this case is say, let's store the models. Instead of returning them, let's actually store them inside a data store in the database because I want to use them later, or I want to pass them to another function and allow them to work with that. So build LM2 also takes Pandas data frame, but it takes a data store name. And so here we're building the same model, but we're going to store that into the data store. So let's run this to create our function. And then we can do the group apply with the data store. So we'll delete the data store my iris species models, right? And then we'll do the group apply execution here. And yes, this is data store not found because we had deleted it previously. And the outcome is that we have 3 models that are produced inside the data store, the Setosa, Versicolor, and Virginica. Something else we can do is we can load the data store into memory directly because we might want to use it locally at our client. And so in this case, we can say ds load and give the name of the data store. And then if we look at the model that's immediately available to us as a variable, we have mod underscore Versicolor. And that's what we can then look at to see that. Of course, we can delete the data store that we just created, and then that's gone. Images. Images are really important in data science, right? We need to be able to return images from our operations. And so this next example, which some of you may have seen from previous presentations, called random red dots, is one that says, I want to generate 2 images and also a data frame of some sort. Trivial in this case, but it illustrates the point. And I also want to show that I can pass in arguments to my function, in this case num.1 and num.2, saying how many dots I'd like created. And let's store this in the Python script repository, right? So we're going to incorporate that there and then print out our list. And we can see that indeed we have random red dots available, and we've just added that to our listing. So,
hey Mark, sorry, just a time check. We're 5 minutes over.
Okay.
We still have a solid group of participants. So.
Okay, that's good to know. Thank you. We should be wrapping up in about, I'd say 5 minutes. So random red dots, if we execute this, we end up with the structured result as well as the images. And then we can invoke this using OML do-eval so that it gets processed on the database server side. And when we do this, the images are rendered and returned back to our client so we can see those along with the structured content. And if we want it, we can also pass in arguments. So in this case, let's change the number of dots to 400, and we will get back the resulting images for that. And we see a lot more dots in that case. We can also load our script from the repository and then use it locally. So it's not only something that we can store there and use an embedded execution, but we may want to just bring it back to the client for future work. Okay, so that brings us to the end of the demonstration on the notebook side of things. What I'd like to do now is to jump to the SQL developer side and show you how we can invoke this from SQL in there, because it's the ultimate deployment approach that we'd like to take with this. So I'll just be bringing that up in a moment, and then we'll wrap up the presentation. In this case, we're going to connect to our database. We have the PyQ user, so we're going to connect to the same one that we were using from the notebook. And in this case, I am illustrating how we can create a new function, randomRedDots2, just to change its name, that does the exact same thing, but we're going to be able to create this function from Python, okay? And then we can invoke a select statement to retrieve the images by saying we want to get the PNG images, and we're going to invoke randomRedDots2. When I invoke this, I get back 2 blobs in a table that I can then inspect directly through SQL Developer. And that's what we'd expect from the result. If we want the structured content, we can specify that it should look like the select one ID and one val from dual. That would be the description of the result. And when I execute that, I actually get back the structured table. And I can join this with others or save it, materialize it as a database table. Finally, we have XML. If you'd like both the image and the structured content, that can come back as an XML string. And so you would have first the structured content, and then you'd have a CData that contains the base64 encoding of the image. Just to say that you can really work whether you're from SQL or from Python. We can invoke the original randomRedDots function just as we did before. So it doesn't matter whether you've created the function from Python or from SQL, you can invoke it all the same. And so this is consistent with that. If you wanted to change the number of dots that are produced, so you change the arguments to our function, you can specify that as a select statement, again, using the from dual capability. And this will change the images that we get back from that. Here we see a lot more dots in that case. So that essentially brings our demonstration to a close. Marcus, is there anything else that you'd like to cover before we adjourn?
No, one last question I was answering it right now is how it compares to OCI data science, because of the people seeing that there is an overlap. I would argue, and you, Mark, jump in, I would argue these are probably complementary solutions where the OCI data science focus on open source algorithms and distributing processing using that kind of interfaces. We are focusing on in-database processing and in-database algorithms, right, that would scale with your database and where you don't need to necessarily move the data out of the database.
Yeah, I think the complementary notion is exactly right, because OCI data science is targeting sort of the open source and outside the database data. So if you have things in, say, cloud storage or elsewhere, that you would work directly with that. However, there will be an integration between the OML for Pi and the OCI data science, because there are times when you will want to work with the data directly in Oracle database. If you're working in that environment, you shouldn't have to pull that data out to go forward. And so that's where there will be the package for OML for Pi readily available to the OCI data science users. And that will be a really nice sort of symbiotic environment. Any other questions?
Excellent. Yeah, I think that's it. We had a lot of questions in the chat. I'll be transferring them to the sessions as well, so people can look look at the answers again there.
Okay, great. Well, thank you all for your attention, and I hope you got as much out of this as you had hoped. And we look forward to hearing from you in the future.
Thank you, everyone, and see you guys in February. Thanks a lot, Mark.
Okay, thank you, Marcus. Bye-bye.
Thank you.